Hey guys, so welcome back. So what we want to do now is apply this new idea of the standard molar volume of a gas to solve some very simple calculations at first, and then we will use more complex calculations as we go forward. Okay, so if you look at assignment 1, these are just some very basic problems that allow us to convert from moles to liters and so back and forth. Okay, so we still want to use dimensional analysis here, and it gives you the conversion factor. So just think about it like converting centimeters to inches or grams to moles. We have a conversion factor. We can use dimensional analysis pretty easily. Okay. So I have 7.08 grams of nitrogen gas at STP. I want to know the volume. So I have 7.08 moles of N2. So I drop the units down. Moles of N2, and I want to convert to liters of N2. So I need a conversion factor, and I have that. There are 22.4 liters in 1 mole, and I'm allowed to do that because it says at STP. So moles and moles cancel, so I get the answer of 159 liters. Okay. So let's look at the next one. I have a volume of 14.1 liters. I want to know how many moles of gas are present at STP. So it's kind of the reverse calculation. So I have 14.1 liters of H2. Drop the units down, liters of H2, moles of H2. I know there are 22.4 liters in 1 mole at STP. Tap in the calculator and you get there are 0.629 moles. Okay. So I think you get the gist there. Let's take it one step further. I want to know number 3, what is the volume in liters of 0.0170 grams of H2S at STP? So I'm given grams here. I don't have a conversion factor between grams and volume because the number of grams per liter varies greatly depending on the gas. So I first have to convert from grams to moles, but I can do that pretty easily. 0.0170 grams H2S. So I've got to convert from grams to moles. So grams H2S, 1 mole. H2S, if you add up the molar mass of H2S, you should get 34.09, or something very similar there. So now I have moles, and I can convert from moles to liters. I know 1 mole of H2S is 22.4 liters of H2S. Okay. So my units cancel, grams, grams, moles, moles. I'm left with liters. When you do the math, you end up with 0.012 liters there. Okay. So the last one, we'll start off with volume in milliliters. And I want to know the mass in grams, so I have to add one more step. So I start off with 15.0 milliliters of SO2. And so I can't work with milliliters, I have to convert to liters first. Okay. So I have liters of SO2, milliliters of SO2. Okay, so hopefully you know there are 1,000 milliliters in a liter, or you can write there are 10 to the negative 3 liters in 1 milliliter. Either way you get the same answer there. So now I'm in liters. Sorry, I wrote that completely backwards. Let me try that again. That's what I get for trying to talk and write at the same time. Okay. Let's try that again. That's what I get for not dropping my units now. Okay, so I have milliliters of SO2 on the bottom because the units drop down. Then on top I'll have liters of SO2. Okay. So now on the top I can have 10 to the negative 3, and on the bottom I have 1. Sorry it's messy there. The other way to do that is to put 1,000 on the bottom and 1 on the top. Or if before you start, you want to go ahead and just divide 15 divided by 1,000 and convert to liters, that's perfectly okay. So now I have a number in liters, and I want to convert from liters to moles. So I know there are 22.4 liters of SO2 and 1 mole of SO2. And now I need to take my final answer to grams because it asked me for grams. So 1 mole of SO2. If you add it up, you should get is 64.07 grams of SO2. Okay? So the units now cancel: milliliters, milliliters, liters, liters, moles, moles. So that's why it's good to cancel your units and check. If I had done that, I would have caught my mistake in the beginning. So be sure that you cancel your units and make sure you don't make any mistakes there. Okay? So now at this point you can go ahead and answer 5, 6, 7, 8, and 9. They are very simple, straightforward calculations, but they are very good practice because now we're going to start using these for a little more complicated calculations, okay? So go ahead and pause the video and work 5 through 9, and the answers are typed at the end of the problem, so you should get the correct answer there. Then you can start the video back, and we will look at assignment number 2. Okay, so assignment number 2 is just some very simple stoichiometry calculations that I think you could figure out on your own, but I'll take you through a couple of them. Let's read one of the problems first. How many liters of ammonia gas can be formed from the reaction of 150 liters of hydrogen gas? Assume that there is complete reaction of hydrogen with excess nitrogen gas and that all measurements are made at the same temperature and pressure. So the equation, it didn't give it to you here, but it is N2 plus H2 yields NH3. So I need a 2 there, and I need to balance it, so I need to put a 3 there. So now I have 2 nitrogens on each side, and I have 6 hydrogens on each side. So it tells me that I have 150 liters of ammonia, or excuse me, I have 150 milliliters, excuse me, sorry, I'm struggling today, 150 liters of hydrogen, and I want to know how much ammonia that I can make if I have excess nitrogen, okay? So this is a little shortcut that we can use to convert straight from liters to liters if we're at a constant temperature and pressure, okay? So I know that in this situation 3 moles of hydrogen produce 2 moles of ammonia, or I could also say at constant temperature and pressure 3 liters of hydrogen also produce 2 liters of ammonia. So let's set it up like that. So if I start off with 150 liters of hydrogen, okay, so normally the first step would be to convert from liters to moles, okay? And we could do that here. We could use 22.4 to convert from liters to moles. So let's go ahead and do that just for the sake of it here. So I can say there are 22.4 liters of H2 and 1 mole of H2. Now I can do the mole ratio step, and I can say that 3 moles of H2 produce 2 moles of NH3. And I want my answer in liters, and I'll convert back to moles. Okay, so I say, excuse me, I want my answer in liters, so I convert from moles to liters. So now I can say 1 mole of NH3 is 22.4 liters of NH3. Okay. So at this point, you can probably see that this and this cancel. Okay. So as long as we have constant temperature and pressure, we can leave off these steps and go directly from our volume into our mole ratio. Okay, so that would be much easier. But you get the same answer either way. But I cannot stress this enough. These volume to volume stoichiometry calculations only work if we have a constant temperature and pressure. Okay, so be sure you underline that several times, constant temperature and pressure. And in this problem, I didn't even tell you standard temperature and pressure. So it's really not okay to use 22.4 unless we are at standard temperature and pressure. So I shouldn't have done that. I just did it there to show you why we're able to do this, okay? But unless it says standard temperature, so we'll just pretend it does, we wouldn't be able to do that. So here we would just go straight to that and get the same answer there, okay? So let's go ahead and look at number 2. Given the reaction, if 5 liters of N2O5 decomposes, how many liters of NO2 can be produced at the same temperature and pressure? So it gives you the blanks there to remind you we need to balance. So I can put a 2 there, I can put a 4 there. So now I have 4 nitrogens, 10 oxygens, and I have 10 oxygens right here. Okay? So I have 5.00 liters N2O5. Okay, and it doesn't say standard temperature and pressure, but it says the same temperature and pressure. So if it says the same temperature and pressure, I can go straight to my mole ratio step, and I can use my volumes as my ratio. So I can now say that 2 liters of N2O5 produce 4 liters of NO2. So that goes back to our previous idea from down here, that we have this equivalency that exists between liters and number of moles at a constant pressure. So you type that in, or you do it in your head, and you get 10 liters there, okay? So go ahead and pause the video, do 3 through 7 these calculations. They should be very simple, very straightforward. But I cannot stress enough how important it is that you notice in every problem that says same temperature and pressure, okay? The shortcut where we use the volume ratio in these calculations only applies at the same temperature and pressure, okay? So go ahead and pause the video, try those calculations, and come back, then we'll look at assignment number 3 together. Okay, so hopefully assignment number 2 wasn't much of an issue for you. We can go ahead and look at assignment number 3 now, and it just takes it kind of one step further. Now it gives us not just the same temperature and pressure, but standard temperature and pressure. So if it's always a standard temperature and pressure, it's going to be the same. Okay, but this allows us to one more conversion factor. We can now convert from liters to moles, and then we could even go ahead and convert from moles to grams. Okay, let's read this problem. Solid iron 3 hydroxide decomposes. Let's go ahead and write the reaction. So FeOH3 decomposes to produce iron 3 oxide. So Fe2O3 plus water vapor. If 0.75 liters of water vapor is produced at STP, how many grams of iron 3 hydroxide were used? Okay, so we cannot use the simple liter to liter conversion here as in the past, because my product or reactant in this case is a solid. Okay, so that conversion factor only works for gases at the same temperature and pressure, so I can't do that here. But I do have a conversion factor that allows me to convert from liters to moles, so I can do that. Okay, so if I start off with 0.75 liters of water, so this is very similar to if I gave you a stoichiometry problem with grams. The first step would be convert from grams to moles. So now we just got to convert from liters to moles. So at STP, there are 22.4 liters of water and 1 mole of water. I use my mole ratio. So something I didn't do up here that I have to do, you have to go ahead and balance the reaction. Okay, so we have 2 here, 1 there, and a 3 there. So now we have 6 hydrogens on each side, 2 irons on each side, and 6 oxygens on each side. So my mole ratio, 3 moles of H2O. And I'm solving for grams of iron 3 hydroxide. So that is 2 moles of FeOH3. And my question asks for grams, so I can pretty easily convert from moles to grams from our last step. So 1 mole of FeOH3 gives me, if you add up the molar mass of FeOH3, you should get 106.88. So before I type it in, I go back and double check my units. I have liters over liters, moles over moles, moles of FeOH3 over moles of FeOH3, and I'm left with grams, and my units cancel out there. So let's go ahead and type this in, see what we get. Okay, so I got 2.4, which matches the number we're given here, so we're in good shape. 2.4 grams, and I should write the units 2.4 grams of FeOH3. Okay, so hopefully you see the difference here in this problem versus the last problem. There are 2 key differences. First, it tells me at STP, so I'm able to use this conversion factor. And it also involves states of matter other than gases, so we have to solve for grams there, okay? So number 2, how many grams of iron 3 oxide were produced at STP? So we really have 2 options here, okay? So option A, which is what the problem intends for you to do, is to convert from 0.75 liters of water to 2.03 grams of iron oxide. Sorry, I misspoke there. What I want you to do is take 0.75 liters of water and convert that to grams of iron 3 oxide and see how much you get. The other option would be to take your answer from A, grams of FeOH3, and convert that to grams of iron oxide. Either way, you should get the same answer. But if you miss A and you use that number, you're going to get B wrong automatically. So I think it's best to go back to the original problem and take that number. To to Fe2O3. I don't know why I keep saying 2.3 there. So let's start off 0.75 liters of H2O. So then I have 22.4 liters of H2O is 1 mole of H2O, and this is true because it's at STP. So I have 3 moles of H2O from the mole ratio, corresponds to 1 mole of Fe2O3. Then it asks for it in grams, so I have 1 mole of Fe2O3 is equal to 159.70 grams Fe2O3. And so I double check myself, make sure the units cancel. They do, so I type in the calculator, see what I get. So 0.75 times 1 times 1 times 159.7 divided by 22.4 divided by 3, and I get 1.8, which matches the answer there. So it equals 1.8 grams Fe2O3. Okay. So hopefully that's pretty straightforward. Go ahead and pause the video, or stop the video rather, and do questions 3 through 7. You should not have an issue solving those there. They're the exact same thing as we've done before with stoichiometry. The only difference is now we have a new conversion factor. So we can convert from moles to liters and liters to moles, but only when we're at STP, okay? So this just allows us a way to get an answer in units of volume rather than units of mass, okay? So hopefully 3 through 7 don't give you any problems. If they do, feel free to send me an email, ask questions, and the answer is typed at the end of every problem, okay? Hope you have a good rest of your week.